Okay, we've been talking about gravitational potential energy and what happens when things are farther away from Earth. Now I want to talk about something that Newton kind of came up with thinking about, and that is he came up with this theoretical experiment, and we call it Newton's cannon. And he said, what if he knew about projectile motion and knew what would happen? And he said, what if we bring a cannon up to the highest mountain we can and shoot this cannon and see what happens. Now he didn't do it; it's a thought experiment. But if you shoot this cannon, you know that it's going to have a parabolic trajectory, and it's going to take a certain amount of time to get down. He said, "Well, what if we shoot it faster?" Well, if we shoot it faster, it's still going to take the same amount of time to get down, but it's still going to go on a parabola and end up landing. But then he said, let's look at it in a bigger context. What happens if I shoot it so fast that it goes so far that as it falls, its fall matches the curvature of the earth? So that the height of the mountain and the height of the projectile at any point stay the same amount above the ground. And he thought there must be some speed that we can do this. That the curvature of the earth, he knew the earth was spherical, at least that's what some people think. And he said the curvature of the earth has to match the curvature of the projectile going down, so that for every meter the projectile drops, the earth's curvature has dropped a meter, so it doesn't drop any closer to the surface of the earth. And he came up with what we call Newton's cannon thought experiment, and that's what we have here. And said if we shoot it fast enough, it should be able to circle the earth and come back to where it initially started. So the question is, how fast would that have to be? So he knew that it depended on the mass of the object, the mass of the earth, and the distance they are away from each other, the center of the earth to the center of the object, because he developed that universal law of gravitation. He also knew about centripetal force and centripetal motion. He did not, of course, have big G. That came around after Cavendish figured it out. So he never did figure it out, but he thought there must be a speed that it has to go to get a low altitude orbit. That's what we would call this. So Newton proposed that orbit was a possibility. Now we know, obviously, that it is. And what we do to figure out what is called orbital velocity is take the universal law of gravitation and set it equal to centripetal force. Because if something's going around the Earth, it's like a circle. If something's orbiting the Earth, it's like a circle. And the force that's pulling that object to the Earth is the gravitational force. It's also considered a centripetal force. So the object's mass is in each of these and cancels out. So the mass of the Earth is a constant. This radius of orbit and r, this orbit radius here and r are the same. So the only variable is the velocity. In other words, the mass of the object that orbits doesn't matter as long as it attains the correct velocity. And that's what we call orbital velocity. Here's our formula for orbital velocity. Notice it depends on the mass of the Earth and how far away from the center of the Earth we are. So Newton proposed that this was a possibility. Now we know that it is. Obviously, we have things in orbit, so we have the ability to send things in orbit. So what we do is send things straight out from the Earth. And let me just draw this here. So you send something straight out from the Earth, and then we give it a horizontal velocity enough so that as it falls to the Earth, it's continuously falling, but it never lands. It stays the same distance away from the Earth the whole time. All right. And that velocity that is attained right there is orbital velocity. So whenever we send a satellite out, we send it up to the orbit that we want, turn it sideways, and give it enough thrust to attain the velocity that we need it to have to orbit. So it doesn't matter what the mass is, other than the fact that it would take more fuel or more energy to get it up to the speed. But once it's at the speed, it can maintain orbit. That's why we can send something like the International Space Station out there and not have it collapse down to Earth until we're ready for it to do that in a few years. And what we'll do is slow it down, and it will spiral in towards Earth, and as it hits the atmosphere, it'll get more and more friction, and it'll burn up in the atmosphere. All right. So let's look at how much force it takes, or how much velocity it takes to have something going at the Earth's surface in orbit around the Earth. Okay. So we know the mass of the Earth, we know G, and we know the radius of the Earth. So using those three variables, we can plug those into this formula. 6.67 times 10 to the negative 11 times the mass of the Earth, 5.97 times 10 to the 24. I probably should have put units in here. Divided by 6.37 times 10 to the 6. And then we take the square root, and we get approximately almost 8 kilometers per second. So if we were to, that's about 5 miles. So if we were to shoot something so fast that in 1 second after we shoot it, it's passing 494, it would have enough velocity to maintain orbit around the Earth. Now, obviously, at this level, it's going to have hills and trees and obstacles, so it's not going to work. So that's why Newton said, what if we went up to a tall mountain? But going up to a tall mountain isn't going to solve it either, because there's other mountains that are just as tall. We'd have to go to Mount Chimborazo, which is the farthest spot from the center of the Earth, and do it. And then we still have to maintain that orbit. And with air resistance and friction, we haven't taken that into account. So we would have to maintain the orbit. Once we didn't have anything like that, then it would just stay in orbit. All right. So that's what we're looking at there. Now, when something's in orbit, it appears weightless. Now, is there weight? Absolutely. Weightlessness is the appearance of no weight because we are falling. An orbit is a free fall. So when something is falling, if we're falling inside something, the walls around us have no way to support our weight. So weightlessness is not the absence of weight. There is no such thing as that. We know based on the universal law of gravitation that there's no point in the universe where we don't have a force of attraction between us and the Earth, or us and any other particle of matter. But the appearance of weightlessness, which NASA calls microgravity, is when your surroundings cannot support your weight. So this dog here floating around doesn't have anything to support its weight in the space capsule, so it's just floating away. Now, I'll show you some videos of some other animals that do not like weightlessness. Dogs are pretty chill about it sometimes, but cats do not like it. So I'll show you a video of cats in weightlessness and show you how little they appreciate that. All right. But it's not a matter of not having a force of attraction. It's a matter of you're inside something that's also falling. So there's no up or down because there's nothing to support your weight. All right. Now, let's talk beyond orbit. Let's talk about escaping the Earth's gravitational pull. Now we know that the Earth's pull of gravity affects us no matter where we are. We cannot get away from it. But what we can do is look at, if you recall, the slide that we had a couple slides ago, which was this one right here. We take the potential energy, GMM over R. negative GMM over R. Well, we can set that. Remember, potential energy reaches zero when you're an infinite distance away. If R goes to infinity, U goes to zero, all right? So what we have to do is find a spot or find a velocity where it has the same amount of energy as the potential energy at that point. In other words, we have to find a kinetic energy equal to that potential energy. So that's what we're looking at. Escape velocity is found by taking the formula U equals negative G M over R and setting it equal to 1/2 mv squared. This m cancels out, all right? And we can see then that v squared equals gm 2gm over r. So v escape velocity is 2gm over r underneath the radical. Very similar to our formula that we had for orbital velocity. The only difference is that it's got radical 2 in it. Radical gm over r versus radical 2 gm over r. All right? It's found a different way. Orbital velocity is found by taking centripetal force and setting it equal to gravitational force, while escape velocity is found by taking the conservation of energy and finding the velocity that will give it enough energy to match the potential energy at a certain distance away from the Earth, or a certain distance away from anything for that matter. It is not escaping the actual gravitational pull. What escape velocity actually means is that if it can attain that velocity moving away from the object, and if it never had any more energy added to it, it would keep moving away from that object, even though it would slow down, but it would move away infinitely and slow down infinitely slow. So an infinite distance away, it would come to a stop, but obviously it never gets to infinite distance away, so it never gets pulled back. That's what escape velocity means. So we can use that, again, to calculate how fast it needs to be going from the surface of the Earth. Now, if we can get something farther away from the surface of the Earth and give it a velocity, it takes less because r is a bigger number, which means the escape velocity is smaller. Okay, but we can use the same exact numbers that we did for finding the orbital velocity at the surface of the Earth, but now we have the different formula. Okay, the only difference is that it's radical 2 instead of radical 2 gm over r instead of just radical gm over r. And we find that it is about 11.2 kilometers per second, about 8 miles per second. All right, so if we shoot something and it passes the Mall of America, 1 second later, it has enough velocity to continue going out of the atmosphere, away from the Earth, and never come back. All right, now, the fact that the only difference between the two is the 2 in there means that you could just take orbital velocity and multiply it by radical 2, and that will give you escape velocity as well. So if you can solve for one, you can solve for the other. And so orbital velocity is times radical 2 is escape velocity. All right. Now, escape velocity then brought up the idea, well, can anything have so much gravitational pull that it never has an escape velocity? And people thought of, well, what has the highest velocity? And that's the velocity of light. And this is the concept of black holes. A black hole is a collapsed star that has such a high gravitational field force that even at that point, the velocity of light, which is the fastest known velocity of anything, does not have enough velocity to escape. All right. So the velocity of light is 300 million meters per second, 3 times 10 to the 8 meters per second. And so if our sun, which is 300,000 times more massive than the Earth, were to collapse into the size of a black hole, how big would its radius be if it were a black hole? Now, keep in mind, it's 300,000 times more massive than the Earth. So we know the mass of the sun, 1.99 times 10 to the 30 kilograms. Escape velocity is 3 times 10 to the 8 meters per second. So we set that to be the escape velocity. We have the mass, we have g. So now we're just finding r. How big would the sun have to be? And it would have to collapse down to this size. Okay? And when we set that up, we rearrange it to solve for r and solve for that, and the radius of the sun would be less than 3 kilometers. So if you think about how massive the Earth is, the most massive thing that we can even relate to at all, which is still hard to relate to, this is 300,000 times more massive. And now it's from here to, I don't know, let's see, 3 kilometers, that's about 2 miles. So about 4 miles from one side to the other side of the sun, and that would be what's going on. So it's such a dense object that it just pulls everything in towards itself even more and more and more. Now, the point where it becomes a black hole is called the Schwarzschild radius. You don't have to know that, but that's where it would become a black hole. So in other words, the sun could be smaller than that, but at 2.9 or 2,950 meters, that's the point where it would become a black hole. Anything outside of that could possibly have enough velocity to escape it. All right. So that's what I wanted to talk about today. And I hope you guys have a good day, and I will talk to you in the next day to come. Thanks a lot.